This is going to be a pretty quick little review for your Chapter 4 test. The first question that I wanted to go over was a mean value theorem question. Find all values of c that satisfy the conclusion of the mean value theorem for this function, f of x equals 1 over 1 plus x on the interval 0 to 1. And so the first thing that we have to do before we can ever even use the mean value theorem is to state that our function is continuous and differentiable on our interval. Otherwise, we can't use the mean value theorem. Don't forget that this is critical. You will lose points because you cannot use the mean value theorem unless you state those things. So we'll start with, since our function is continuous and differentiable on the interval 0, 1, we can use the mean value theorem. And just look at this, we know that this fails differentiability at x equals -1 because our denominator can't be 0 in this case. So that's not on our interval. So we're good to go and we can use the mean value theorem. Okay, now that we have done that continuous and differentiable thing, and please do not forget that, you will lose points. Now the mean value theorem says that our slope equals our derivative somewhere, and we have to find that c. So let's do the slope first. The slope is just going to be f of 1 minus f of 0 all over 1 minus 0. If I put in a 1, I get 1 over 2 minus, if I put in a 0, I get 1 over 1 all over 1 minus 0. So that is simply -1/2. And then our derivative, f prime of c, I'm just going to do. Well, in order to do this, I either need to do a quotient rule, or I could rewrite this, and I'm just going to rewrite this as 1 plus x to the -1st power. And now I'm just going to use a chain rule where that's my baby, the 1 plus x. And so I get -1 plus x to the -2 power times the derivative of the baby, and the derivative of 1 plus x is just 0 plus 1. Nice and easy there. So, oops, and I said f prime of c, so I should make that a c. -1 over 1 plus c, the quantity squared. Now, I'm not being particular. You can leave this as f prime of x and put these all as x's. I just want to find this value c here since that problem's asking me that, so I'm just doing a c. Anyway, now I'm going to set my slope equal to my derivative. So I have -1 over 1 plus c, the quantity squared, equals -1/2. Now listen up, because here is a really good trick, okay? I have the numerators are the same, the -1. So I know that the denominators must be equal, right? Okay, now everybody's always tempted to FOIL this thing out, but why would I do that when I want to solve for c? Why don't I just take the square root of both sides? I'm allowed to do that, right? And so I get c equals -1 plus or minus √2. And if I had -1 minus √2, that's definitely less than 0. So I'm going to cross that answer out because it's not in my interval. And so the only c value that I find is -1 plus √2. And that is between 0 and 1. Because remember, √2 is some number between √1 and √4, which is between 1 and 2. And so that would definitely be greater than 0, but still less than 1. And so that's my answer. And you didn't forget to write that part, right? Okay, so pay close attention to that question and exactly how I solved it here and what I explained here. If you didn't get that the first time, go back and watch. Hint, hint. So now let's do a related rates question with a cylinder. So the radius of a right circular cylinder, so I'm going to just draw the cylinder. The radius increases at a rate, so that's my dr dt, 0.01, and let me just check my units. I have centimeters per second, I have centimeters per second, I have centimeters cubed per second, centimeters cubed per second, and centimeters. So I'm all in the same units. I'm good to go. Don't need to worry about that. So dr dt is 0.1, and the height decreases. So it's decreases, dh dt is negative because it's decreasing at 0.2 centimeters per second. What is the rate of change of the volume of the cylinder? So I want dv dt is what? When the radius is 2 and the volume is 12 pi. Okay, so I want to find dv dt. So what is my volume? My volume is pi r squared h. And I know in this problem that my volume, my radius, and my height are all changing over time. So I need a product rule because I have pi r squared times h. So dv dt is pi 2r dr dt. Remember, the radius was changing over time, so it has a baby, times h, derivative of the first times the second, plus the first times the derivative of the second, and the derivative of h is just dh dt. Okay, so I want to find dv dt, and I know pi times 2, I know my radius is 2, my dr dt is 0.1. But what is my h? I'm not really sure. But they gave me this piece of information which I haven't used yet. My volume, remember, is pi r squared h. So when my volume is 12 pi, I know that my radius is 2 because they told me that. So what is my height at that moment? Well, 12 pi divided by 4 pi is 3. So my height at that moment is 3. So that is the height we're going to use. Pi r squared, and my dHdt was negative 0.2. And then you just put all that stuff in your calculator. I'm going to let the pi hang out and put everything else in my calculator. And I get negative 0.4. So I'm going to just say negative 2/5 pi, and it's fine if you write it as a decimal too, but we do need units, and our units are going to be centimeters cubed per second. And you know what? This is actually a typo here. I'm just realizing this. It says the volume is 12 pi. That's not a rate. That should just be 12 pi centimeters cubed, right? That's the volume. It's not a rate. Our dv dt is a rate. So that is our answer. Now let's do a cost minimization problem. So we have this cylindrical can, and it's supposed to hold 108. So that's the volume. It's inches cubed, so that's an indicator that's my volume. 108 pi cubic inches. The cost of the material to make the top and the bottom is $4 per square inch. So the top and the bottom are going to cost that much, and the cost to make the curved side is $2. Find the radius and the height. That's the cost of making the can. So what do I want to minimize in this question? I want to minimize the cost equation. And what is that cost? That cost is going to be the material that I have. So I have pi r squared for the top and the bottom, right? That's how much area I have to cover. So we have the pi r squared, but we have it on the top and the bottom, so we have 2 of them. And how much did it cost? The cost to make the top and the bottom is 4. So that is $4 for that amount. And I have $2 for the siding. And what is the siding? Remember how we did this and we like rolled the thing out, like if you had a label on a can, and this side length is this round part, which is the circumference, which is 2 pi r, and then this is just the height of my can, that thing. So the area would be 2 pi r h, right? So $2 is the $2 here, and this is the area of my side. And this is the $4, and this is the area of my top and the area of my bottom. So that's how I come up with that cost equation. Okay, so now I can simplify this down a bit, and I get 8 pi r squared plus 4 pi r h, which is excellent. But remember, before I take a derivative here, which is ultimately what I want to do, before I do that, I want to use my helper equation to get everything in one variable. So my goal is probably to get everything in terms of r in this case. So here's going to be my helper right here. I know that my volume is 108 pi. And I know that the volume of this is simply pi r squared h. And so let's solve for the h so that I can get rid of the h. I just want r's. So h is going to be 108 pi over pi r squared. In other words, 108 over r squared. So I use this as my helper to help me get the cost in only one variable. 8 pi r squared plus 4 pi r, and instead of h, I'm going to use 108 over r squared. And so I'm left with 8 pi r squared plus 432 pi. R divided by r squared is just r. Because I'm going to take a derivative, I should have probably written this as r to the -1, so I'm going to just go ahead and do that right now. Now, in order to minimize, I'm going to want to take a derivative and find my critical values. So c prime equals 16 pi r minus 432 pi r to the -2. Let's get a common denominator here. So I have 16 pi r minus 432 pi over r squared. My common denominator is going to be that r squared. So since I put an r squared on the bottom here, I need to multiply by r squared on the top, which is going to give me 16 pi r cubed. R times r squared is r cubed minus 432 pi. So now my critical values are going to be where c prime equals 0 or where c prime does not exist. C prime equals 0 if my numerator equals 0. $432 divided by 16 is 27, which is very lovely, so that r is 3. And it does not exist when the bottom, r squared equals 0, r equals 0, which doesn't make sense in this problem. My radius can't be 0. I wouldn't have a can going on at all. So they just want the radius and the height. So the radius is going to be 3 inches, and the height is going to be 108 over 9. Because 3 squared is 9, and that's 12 inches, and that is the dimensions that minimize the cost of making this can. I really don't have any endpoints to check in this problem because the endpoints would have made no can at all. So that's really all I have to do in this problem. Now let's look at this problem, which was from your optimization worksheet number 3. Let's maximize the volume. We have this sheet of cardboard that is 3 by 4, and we are going to make it into a box by cutting out sides x by x in this case. So when we do that, we are left with this side is 4 minus x, which is 4 minus 2x. And then this side here is going to be 3 minus 2x. And so I'm going to fold those sides up so the height is x. One side is 4 minus 2x, the other side is 3 minus 2x. The volume is length times width times height. Now, in order to find the dimensions with the largest volume, I'm going to want to maximize that volume equation and take its derivative. I personally like to simplify this completely out before taking a derivative. Otherwise, I need a double product rule, which I don't want to do. So I am going to FOIL first. And then I'm going to distribute that x out. At this point, I can take a derivative pretty easily. So I have 12 minus 28x plus 12x squared. I can take a 4 out of all of it. And I'm going to just rearrange things. So I'm going to put this first. So I have 3x squared minus 28 divided by 4 is 7x plus 12 divided by 4 is 3. So let's see if we can factor this. 3x and x, and nope, that baby is not going to be factoring nicely for us, so we need a quadratic formula. So I'm going to just use this here, negative b plus or minus the square root of b squared minus 4ac all over 2a. And we get 0.566 and 1.768. And I really should have looked at my domain restrictions before I started. What do we know? Well, we know that the side length has to be greater than 0, strictly greater than 0. And which one is my shorter side? The 3 minus 2x. So I know that that 3 minus 2x must also be greater than 0. So that means that 3 has to be greater than 2x. In other words, x must be less than 1.5, right? So this one is not possible. Only this one. And if I had made my number line, I would have found that one maximized and one minimized, and I want to find the largest volume, so that would have happened also. But my restriction is that my x value must be between 0 and 3/2. Okay, so now we want to find the dimensions of the box with the largest volume. So that's pretty easy. We know that x is 0.566 feet. Then our other side is 3 minus 2x, which is going to be 1.868 feet. And then we have 4 minus 2x as our last side, which is 2.868 feet. And so the dimensions are simply 0.566 by 1.868 by 2.868. And that's it. Our last question here is that we have this piece of wire that is 60 centimeters. So this whole thing is 60 centimeters, and we are going to be cutting it into 2 pieces. And the first piece is going to form a rectangle, and the second piece is going to form a square. What do we know about the rectangle? The rectangle is 5 times as wide as it is long. And then, of course, we have a square, and that's all y by y by y by y. Now, there are multiple ways to set up this problem. I like to just set it up as, here's my rectangle, and I'm going to put that in x, and here's my square, and I'm going to put that in y, and then I'm going to use this information that I have that all of this material plus all of this material must be 60. In other words, 5x plus x plus 5x plus x, which is 10x and 2x, and then y and y and y and y, which is 4y, must be 60 since I have 60 centimeters of material. So I have 12x plus 4y being 60. And then I want to know how to minimize and maximize the total area. So I want to optimize, okay, the optimization part. You could have written minimize and then maximize A and B separately. The optimization is going to be on my area equation. So because I'm optimizing this is what I'm taking the derivative of. This is what I want in all of one variable before I take a derivative. That makes me know that this right here is going to be my helper because it's my other equation, right? So the area is, I have to add the area of this and the area of that separately. So I have 5x times x plus y times y, which is 5x squared plus y squared. So now I think that I will just get everything in the x variable. So I'm going to solve for y. For y equals 60 minus 12x. Y equals 15 minus 3x. So I'm going to substitute that in for the y. Area equals 5x squared plus 15 minus 3x, that whole thing squared. Again, I'm going to simplify before taking a derivative here. Your choice. You could have done a chain rule there if you didn't want to, but I'd rather just FOIL. Minus 90x plus 9x squared. So my area equation, I have 5x squared plus 9x squared, which is 14x squared minus 90x plus 225. At this point, I am going to take a derivative. So a prime is 28x minus 90. A prime equals 0. A prime does not exist. I don't have to worry about it not existing. So don't worry about that. And this is when 28x equals 90, which is when x equals 3.214. Okay, so this is our only critical point, and now we need to look at our endpoints. And our endpoints are really important in this question because we can have all our material used to make just the rectangle, right? And if that were the case, then all would go into this. So I would have 5x plus x plus 5x plus x. I would have the 12x being equal to 60. So the x would be 5. Or I could have all the material used to make just the square. And if that was the case, then none of it would go into here. So my x would just be 0. So those are my endpoints, and I need to compare those to find the minimum and the maximum. So what I'm going to do is I'm going to find the area at the critical values, and I'm going to find the area at the endpoints. Now the area equation I'm going to use is just this simplified thing right here, which is 80.357. If I put in a 0, I would just have 225, right? And if I put in 5, I actually get 125. And so this is the absolute biggest I see, so that's going to maximize, and this is the absolute smallest I see, so that's going to minimize. So back to our question, it says, where should the wire be cut to minimize the total area? So we minimize when x equals 3.214. So that means how much of the material goes into the actual rectangle part here. That would be the 12x. So it would be 38.568, what are my units here, centimeters in. So 38.568 centimeters for the rectangle, and the rest will be used for the square. And it's going to be maximized when the x is 0. So that means that all 60 centimeters are used for the square. So basically, I don't cut my wire at all, and I just use it all to make my square. And that's my answer.